So previously we had talked actually about some more closure properties. I thought I would show us a different operation we could do or consider for a language or a string respectively. Is called reversal. We haven't talked about reversal yet. So let me define it. The reversal of a string W, the A1, A2, suppose these are the symbols, just giving them names. So it's A1, A2, AN minus 1, AN, all the way up to N. There's N symbols. Is the string written backwards. So, i.e., it would just be AN minus 1 down to A2, A1. So let's do a concrete example, just make sure I'm clarifying myself carefully here. If I give you the word kitty, can somebody tell me what the reversal of kitty is? What's the reversal of kitty? So if I give you kitty, this string here, what's the reversal of kitty? Wow, it is Y-T-T-I-K, right? You just take the same string, you write it backwards. So I'm going to denote this reversal like an operation of sorts. We will denote the reversal of a string. String W as W with a capital R in the exponent position. Likewise, denote, so if I have a language now, I could go through each one of the strings. You can imagine I could go through each one of the strings and I give the reversal of that string. I can talk about the reverse of a language. Denote the reverse of a language, L, as L with the capital R in the exponent. So here's what I'm going to show you today, is I'm going to show you how you can obtain the following property. So if L is regular, so this is the claim. If L is regular, so is L reversal. So I'm going to give you a sketch of the proof because I think it's simple enough to play around with. So I'm going to walk through a sketch of how you prove this. So one, you already know that if L is regular, then there is an epsilon NFA M that recognizes L, right? We know this. It's by Kleini's theorem. So namely, we use the subset construction to obtain an equivalent D of A, right? But also note Kleini's theorem also gets us back around. So if ever we need to go the other direction, we can always cut our way through with a regular expression, if need be. But we've already established that subset construction does exactly what we need. Let's say that recognizes L. So we're going to construct a new epsilon NFA from this epsilon NFA. Construct a new epsilon NFA M prime that recognizes LR or L reversal as follows. Now you might ask, Dan, what are you going to do now? What are we going to do? Well, it's going to feel very natural for the operation, right? So you can imagine you have your start state, right? To get from the start state to a final state, you follow a sequence of transitions, which are directed edges, right, or arcs. So a very natural graph theoretic way of thinking about this process is you're exploring the graph by navigating a directed path or directed walk, right? Well, you follow the arrows, right? Well, if I wanted to do this, but in reverse, what do I do with those directed edges then? What do I do with them? I reverse them, right? So that's the first thing I'm going to do. Reverse all the arcs. Reverse all the arcs for transitions of M in M prime. Now, we have to do something about the start state and the final state, right? Make the final state in M prime the start state of M, right? It has to get to the start state. That's where it begins in M. So if we need this new epsilon FA to work properly, I just want to make sure it gets over there. But you might ask, Dan, why do you want to use an epsilon FA? There's one issue that we have not addressed yet. Think about it. Here's just a little doodle. So imagine I have the start state. Imagine there's just some states here that the transitions occur on or something like that. And suppose that some of these are final states, right? Some are final states. Who knows? There could be self loops in here. But say a couple of these are final states. Well, in this construction, it says to reverse all of these, right? You're supposed to reverse all of the arcs, and then you assign the final state in the new epsilon FA to be the start state, right? But here's a bit of a problem, right? There might be multiple final states. So what do I do with these multiple final states then? They surely all can't be a start state, right? You only can have one of those. So what do I do? Well, we're going to do something that is very natural if you think about this in terms of graphs. So if you have multiple final states, well, why don't we try to pretend that all of these final states are actually just one start state? And one way I can do this is by creating a new state that is the new start state of this epsilon FA that I'm building. But I make it so that I can use epsilon transitions so I can freely get to the old final states of the original epsilon FA. So in effect, I am pretending that many final states are actually just one start state. And it's all because of the epsilon move that I'm allowed to take. So create a new start state Q0 prime in M prime, where it transitions on epsilon. It's important that it's epsilon to all the accepting or final states of M. So the accepting states of M. So in M prime, you would just use what those final states would have been. And now those are going to have epsilon moves towards them, completing the construction. Now, here's the other key observation, is You might ask, Dan, well, okay, so what can you do? What can we say about this new epsilon FA M prime? Well, here's the other part of the proof. So once you got this, so M prime simulates in reverse. So I'm going to put that in quotation marks. It's a little small here. It says M prime simulates in reverse. In reverse, M, meaning that M accepts W if and only if M prime accepts W reverse. So I encourage you to pick up an epsilon NFA. So take any one of the examples we played around with in the past. Then what you do is you try to use this construction and see if you end up with exactly what we claimed here. I encourage you to try writing this out more formally, but these are all the key ingredients for the proof. So, that being said, if you go through this carefully, make sure you convince yourself that it is in fact correct. If I give you a regular language L, then its reversal is also regular.